I didn't do a very good job in explaining in the previous video, so now I'm going to re-explain the whole thing again. Um, we started out with a whole family of these graphs. We were trying to find a new type of graph in such a way that is always perpendicular to all the members of this family here. And if we use this here, it will give us a whole family of ellipse. And the whole family of ellipse will always be perpendicular to all the members of this family. Well, alternatively, if you use this here, it will give you a family of ellipse. But then if you differentiate this, it will give you this. But then if you use this here, it will give you a whole family of these logs. And you can see here, it's always 90 degrees here. So the point here is that if we use this, it will give us ellipse. If we use this here, it will give us log. So starting from here, um, so given the whole family of these graphs here, if you differentiate it, it will give you this. But then if we want to try and create something that's perpendicular, we will need to take the negative reciprocal of this. That will then take us to this. Okay, so we would then separate all the variables. So our normal routine, get all the x's on one side, all the y's on the other side. That will then take us to here, and then that will then integrate equally to both sides. That will then give us this here, and that will then give us this. So the point here is that when you get to this stage here, there are two ways of finding the antiderivative of this. One is to one is to try and guess. So you could guess what would differ. So here you would look at this 1 over something. You would visualize this as 1 over something. So your initial guess would be log of something. Now, when you differentiate log of something, it will give you 1 over that bubble there, and then you've got to times by the derivative of the bubble itself. So to find out the antiderivative of this, blah blah blah, that will then take you to here. Okay, but the alternative way of doing this is to realize that so one way of doing it would give us this. Okay, and I've already explained this several times. Now here's another way of doing it. Here you are trying to find the antiderivative of this with respect to x. So you can see here, this is a constant, this is a constant, this is a constant. In fact, the whole thing here is a constant. So you can actually factor this thing out, take it out here, and just well, hang on. Let me show you this here. You can actually take this whole thing out, and then concentrate on well, looking at this here, you can visualize it like this: minus 1 over 2a times 1 over x. So you can visualize this thing here as this dx here, and then you're trying to integrate this. This thing here is just a constant because you're trying to find the antiderivative with respect to x. So you can actually take this thing out and just concentrate on finding the antiderivative of this. So the point here is that one way of doing this will take you to here. Another way of doing this is to look at this here, and then take this bit, take this constant out. That will then take you to here. Okay, so now just concentrate on finding the antiderivative of this, and then that will then give you this. So now this times this times this. So that will then give you this. Okay, so this times this will give you this, and then this times this here. Hang on, let me think. Yeah, this times this here will give you this. But here you've got a constant that you don't really care about, and then you're timesing something that you don't care about. So let's just call this a new constant. By right, I should give it a different name. By right, I should give it a different name, but it's just a constant that we don't really care about. So that will then take you to here. Okay, so you can see that when you're here, there are two ways of finding the antiderivative. One way would give you this. The other way would give you this. Okay, so hang on. So looking at this here, we got to this stage here. If you so one way of finding out the antiderivative of this will give you this. The other way of doing it will give you this. But in fact, the uniqueness theorem says that if something differentiates to the same thing, so for example, this thing here differentiates to the same thing, this thing here differentiates to the same thing, that means these two are exactly the same but only differ by a constant. It's just like you having a derivative of, let's say, 2x, and then here you've got x squared plus 3, and here you've got x squared plus 7. You see, these two differentiate to the same thing here. So if two things differentiate to the same thing, then these two things must be exactly the same, but only differ by a constant. Only differ by a constant. The point here is that this here is exactly the same as this, but only differ by a constant. Okay, so you can see that here. So in the case of remember, we are trying to investigate why we are trying to investigate this whole family here. So let a equals 2. So let's just consider the case when you got y equals 2x squared. Let's just consider a particular case where a equals 2. Okay, so if you looking at this here, if you find the antiderivative, this is one way of doing it. This here is another way of doing it. But then if you get a graph plotter and plot this and this, it will look like this. Hang on, it will look like this. Okay, so here, so the point here is that this here is exactly the same as this, but only differ by a constant. So that means that if you've got a good graph plotter, you do this plus a constant here, and then vary this c. I don't know if you get a good graph plotter, it will allow you to vary this c. So have it in a case of investigate for yourself. Plot a graph of this exact same thing, and then plus 1, and then later change it to 2, and then change it to minus 2, and then you can see this move about. But then in effect, there's a particular C here where this line here will overlay exactly on top of this line here. So the point that I'm trying to make is that this is exactly the same as this, even though they differ. Okay, they're exactly the same, but only differ by a constant. So let me try and illustrate this to you with an animation. So here, so now I'm going to do the same thing but plus c, but then I'm going to vary this c here. Okay, so looking at my graph plotter. Okay, hang on. So so here we've got one graph, and here we've got another one. Let me just look. This is me changing the c. Okay, it's me changing the c, and then you can see that as you change the c, you can see that. Well, I hope you can see this. I hope you can understand what's going on. But this is what happens when you vary the c only, and you can see that it's always at 90 degrees as it moves about. It's always 90 degrees with the 2x squared one. Okay.